So this is the first video in a series of chemistry videos I'm going to be doing. This is a very basic introduction to organic chemistry, and this is just kind of dipping your feet into it, so to speak, and seeing if you like it. So your feedback is greatly appreciated. First of all, let's talk about what organic chemistry is and look at a little bit of a history of organic chemistry. Chemistry as a whole, the science itself started evolving into a modern science in the 1700s. But back then, organic chemistry was used to describe the science of substances derived from living things. And these substances were actually believed to be difficult to manipulate in the laboratory, and it was noted that there was a difference between substances derived from living things and substances derived from like minerals and non-living things. So inorganic chemistry and organic chemistry were noted to in that way, and for about a century. And organic chemistry had a vital life force, and it's what scientists said. About the early 1800s, some scientists started doing some experiments on some organic compounds, and actually found that they could be manipulated in the lab. I think one scientist, I don't remember his name, but he did an experiment with soap and like alkali. I think I want to say it was like sodium hydroxide, and with animal fat, and he separated it into organic compounds and fatty acids. And another scientist later in the 1800s, like 1826 or something, did a experiment, and he involved some kind of inorganic salt and ammonium cyanide, and made a component that was similar to human urine in the lab. And so and this was like synthetic, like urea. He made urea in the lab. And so they started to disprove that organic compounds were only found in nature, that they were difficult to manipulate in the lab. And so they also found that the same principles that applied to inorganic substances also applied to organic substances. So basically, that being said, modern times now, all principles that apply to inorganic substances do apply to organic substances. Chemistry is chemistry. All principles apply across the board. Okay. Organic chemistry now means simply that it involves the carbon element. That's it. And why is carbon special? Of 30 million molecules, 99% contain carbon. Carbon is a 4A element. It has 4 valence electrons. It can form 4 covalent bonds, and it has immense diversity, from very simple molecules like methane gas. You're thinking that doesn't sound simple. It it is. It's carbon and 4 hydrogens, CH4. In organic chemistry, that's actually that's very simple. And we'll get to that. 2 very diverse molecules like DNA. And so many things in between. Fatty acids, which have their own chapter in the book, and synthetics. Everything from morphine to sulfuric acid, all of that. That's organic chemistry. I just named 2 really dangerous substances there. I'm sorry. Wow, my mind's dark today. Sorry. But that's organic chemistry. So if you're interested in learning about that, please do stay tuned. This will be a very, very basic video. We're going to go over the some general basic principles of chemistry, because you have to understand how the valence shells work, how the orbitals fill up in the electrons, what's in an atom. You have to know these things. Things like that. And we're going to talk about sp hybridization and why carbon forms tetrahedral, why it has tetrahedral tendencies. So let's get into that. And if you're interested and if you have any feedback, please let me know, and I will continue to make videos, organic chemistry videos, and see how far into it we get. And I will show you what the next chapter is for each. I'm not going to skip chapters though, because organic chemistry builds layers. You have to go chapter by chapter, and I am using my textbook as reference, and I'm not always going to use my textbook. In this video, I'm going to use it for part of the video, and then I'm going to do my own thing for part of it, but I am going to use it for reference on what to cover next, because it builds. So do keep that in mind, and I will each video show you what is coming up next, and your feedback is greatly appreciated. So I hope you guys enjoy. Let's get into it. Okay. Alright, so let's dive right into organic chemistry. This is the 7th edition. They're actually, I want to say they're on the 9th or 10th edition. And I looked into obtaining that book, and it was close to $200. This one is not terribly outdated. I had it in class in 2009, 2010, maybe they were still using it, I think. Yeah, so the basic gist of it is the same. There might be slight verbiage changes. The biggest difference I noticed was on a video I watched. They had changed bond length. They were measuring it in angstograms as opposed to picometers. And I don't know if that was just the preference of that particular scientist, or if that was actually required to change. And I did not look into that for you guys. I apologize. That's something that perhaps I will do that, and maybe one of you will know that answer. I will refer to them as picometers for now until I figure that out, but I think they might have changed that. So I was just saving my place with this. So this is just my good old CVS pharmacy. But actually, the CVS pharmacy I go to is awful. Funny though, because this is holding a place where I have some synthetically made medicine, not actually any I'm prescribed to, on this page. We're actually not going to, in any near future chemistry lecture, organic chemistry lecture, talk about any of these chemicals. This is just showing you an example. Some of these are naturally occurring organic compounds, and some of these are synthetic. Here we have cholesterol, which is a naturally found organic chemical. And then we have Viagra, which is synthetic, Oxycontin, benzyl penicillin, but we aren't going to talk about that. And this is just saying that some of these names and molecules might be familiar to you, and that organic chemistry is found all around you, from your hair, your skin, your muscles, the proteins, the DNA, and even the medicine that you take. And that anyone who studies biological science needs to understand organic chemistry. This is, sorry you guys, my stomach's growling. And as I stated earlier, there are some car noises, and we will call that city ambient. Alright, so this is actually, Lord help me. Okay, so this is actually what I spoke to you guys about previously, and that is the introduction of organic chemistry and how it was separated from inorganic chemistry, and the vital force, and how it came to be labeled organic. This is one of the first organic chemical reactions in a lab, and it shows how animal fat can actually be broken down to soap and glycerin, and that soap is actually just fatty acids, which is interesting. I'm actually going to be making soap today, and in order to do that, I'm actually going to be mixing sodium hydroxide, which is this chemical component here, with water, and then taking that and mixing it with oil. I'm not using animal fat as my oil though. I'm actually going to be using like coconut oil and other things, but then the sodium hydroxide and water turns to glycerin and it makes soap. So anyway, and then here's the chemical reaction, ammonium cyanate, which with heat breaks down to urea. So we talked about that. Here is the periodic table. Okay. And it shows some of the common elements that mix with carbon. Here is the position of carbon. Okay, and it shows hydrogen commonly mixes with carbon, nitrogen, phosphorus, argon, sulfur, chloride, chlorine, bromine, and iodine. Those all commonly mix with carbon. So that's what that's showing. So let's just dive right in to our basic chemistry. And then what I'm going to do is, when we get to the section of hybridization, I'm I'm going to draw it out for you. I'm going to switch sides and I'm going to draw out the hybridization. It's kind of was a tricky notion for me when I first started organic chemistry. And I think that doing some drawing for you guys will be fun. And so let's break it up that way, shall we? So, atomic structure in the nucleus. This is a very basic chemistry concept, right? We all know that the structure of a chemical element is a nucleus that has neutrons and protons in it. And I'm gonna now show you a picture inserted into the video. So as you saw, there are neutrons that are neutral, protons that are positive charges inside of the nucleus, and then there are electrons that orbit on the outside of the element. Okay, an atom is described by its atomic number. That is the number of protons. Very basic concept. Okay, let's talk about its atomic mass number. Its mass number. Let's talk about its mass number. That is the number of protons and neutrons. Its mass number can change because different elements can have different number of neutrons. For instance, carbon can have what is known as carbon isotopes. It can have different number of neutrons. So what they do on the periodic table is they take the average number of, they take the average, sorry, I can't really see that. They take the average number of the neutrons, and that becomes the weighted average of their isotonic numbers. Okay. So that's what that is. Okay. That comes into play later when you are doing, in the laboratory, when you're doing chemical equations and you need to know the atomic number or the mass number. Okay. Moving on. Let's look at orbitals and electron configuration. So an orbital is basically describes the volume of space around a nucleus that an electron is most likely to occupy. It's the area around the nucleus that you're most likely to find the electron. Okay. There are 4 types of orbitals. An s orbital that's shaped like this, a p orbital that's shaped like a dumbbell, and a d orbital that's shaped like this. And a carbon atom, you're never going to make it to the d orbital. Carbon atoms only go up to the p orbital, so we're just going to focus on the p orbitals. Okay. As you go up in orbitals, you go up in increased energy of the electrons as they move away from the nucleus. They increase in their energy. The orbitals are contained in shells or layers around the nucleus. Okay. Each shell or layer is successfully larger and has more energy. So the first shell around the nucleus is can hold 2 electrons and one s orbital. The second shell can hold 8 electrons and has one s orbital and 3 p orbitals. And that's important because we are going to play around with sp hybridizations here shortly in the carbon molecules. And that is how carbon is able to form so many rings and double bonds and covalent bonds and become tetravalent as well. And that's why carbon is so awesome. Okay. All right. There is a node that separates this the p orbital, the 2 lobes, that is has no electron density, and each lobe, each region has a different algebraic sign. So as you see in the second shell here, where 2p, like one electron would go here and one will go facing that way. But we're not going to look that much further into that. And I actually drew them in that way to show you. Here is the 2. So this is the layer 2 orbitals. And this is how they're drawn in. Okay. So I'm going to read to you very quickly and briefly the rules for electron configuration. Okay. Then I'm going to read to them to you. Are you ready? Rule number 1. The lowest energy orbital, which is 1s, fills up first. So it goes 1s, then 2s, then 2p, then 3s, then 3p. Then actually before 3d fills up, 4s comes in and fills up. I don't know if you guys remember that from basic general chemistry, but before any d orbital fills up, like the s from the next shell starts to fill up. Okay. Note that the 4p orbital lies between the 3p and the 3d orbitals in energy. Rule number 2. Electrons act as if they were spinning around an axis in much the same way that the Earth spins. This spin can have 2 orientations denoted as up and down. Only 2 electrons can occupy an orbital, and they must be of opposite spin. A statement called the Pauli exclusion principle, and that's what we've drawn in here. That's what's being shown here. If 2 or more empty orbitals of equal energy are available, 1 electron occupies, each with spins parallel until all orbitals are half full, a statement called Hund's rule. Some examples of how these rules apply are shown in table 1.1. Hydrogen, for example, has only 1 electron. So it only has 1s. Okay, so let's take a look here. I'm going to try to zoom in, see if you can see that. Maybe I can pick this up and gracefully show it to you this way. Then you look at carbon, see how the 1s fills up first, then the 2s. Then when the 2p starts to fill up, Hund's rule applies. And they have parallel half full orbitals in that shell. So let's look at phosphorus then. Where phosphorus has the 1s fills up, the 2s fills up. The 3p went 1, 1, 1, 2, 2, 2. Okay, then the 3s went boom, then the 3p. Then if it had one more, it would go here, just like that. Okay. Alright, let's see now. Let's see if I have a piece of paper. Okay. How many electrons does each of the following have in its outermost electron shell? Let's try an example. Let's see. Magnesium. Let me find one that's fun for us to do here. Okay. So let's do magnesium has 12 electrons. Okay. So let's draw out our orbitals. Okay, we're going to start with 1s. Okay, 1, 2. Then 2s fills up. 1, 2, 1, 2, 3, 4. Okay, then 2p fills up. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Alright, and then 3s. 1, 2. Now let's check the back and see if we're right. I haven't done this in a while, so just bear with me, okay? Chapter 1, 2. Let's see. Oh, it's stuck together. Oh no. So sorry. Okay, so it says in its outer shell. How many does it have in its outer shell? Its outer shell is 3. Okay, it has 3 shells. 1 shell, 2 shell, 3 shells. It has 3 shells. And it has 2 electrons in its outermost shell. And we are correct, guys. Excellent. Great work. Okay. Alright, so moving on. We're going to talk about chemical bond theory, and I'm going to go through this relatively quickly because I do want to have some time to draw through the hybridization for you, okay? But the chemical bond theory, it basically proposed that carbon is tetravalent, and that means that it always forms 4 bonds when it joins other elements to form stable compounds. And this explains why. Why does it do that? Okay. It means it can share 4 electrons with 4 other elements. It can double back on itself to form double bonds, triple bonds, or carbon rings. Okay, and here's a great picture. Here's carbon, and when it forms just 4 regular bonds, it always is at a particular angle, and we'll explain why that's because of the hybridization. But we're gonna get into that shortly. Okay, bonds on this page, and then this means this is receding into the page and this is coming out of the page. So if you had the carbon molecule floated off the page and it was 3D, if you had the 3D molecule of carbon with 4 hydrogens, which is actually methane, this is methane right here, you would have 2 of them sitting like on the plane, and then you would have one sticking out and one sticking out and one sticking forward. So that is how it would be shaped. Why? So, chemical bonding theory basically states that atoms bond together because the result is lower energy and more stability. Energy flows out of the reaction and it takes energy to break that bond. The noble gases have full outer valence shells. So, they have achieved low energy and ultimate stability. Helium has a number 2. That means that its first S shell is completely full. It is completely stable. Neon is 10. That means that its first S shell is full, and then its second shell, its second S, and its second P is completely full. So it's full. It has achieved complete stability. Now, if you look at the alkali metals in group 1A, they try to mimic the valence electrons. And they do this by losing an S electron and become a cation other than hydrogen, because it only has 1 electron to begin with. And that plays a different role, and actually will just share its electron with pretty much anything. I'm joking, but all jokes aside, let's take sodium for example. Sodium will lose one of its S electrons from its valence shell and become a cation, meaning that it has a positive charge because it's losing an electron. And then the halogens in 7A will gain an electron in its valence shell to fill its shell. And when they do, when this 1A loses an electron, its valence shell, meaning that it's a very outer shell that it has, and that can be different for all atoms depending on how many shells it has. They all have a different number of shells depending on how many electrons they have to begin with. So when the halogens lose an electron, when the alkali metals, lose an electron, their outer shell is full. It then becomes, their outer shell changes, and they don't just have that 1 electron sitting in a new outer shell, and when the halogens gain an electron, their outer shell becomes full. They become an anion. So these halogens actually connect very well to these alkali metals. And that's an ionic bond, because this cation will bond with this anion. Because this will have a positive charge and this will have a negative charge. And this, like sodium chloride, well, that's salt, potassium bromide, sodium iodide, whatever. So, but elements in the middle, or say for instance carbon, it has 4 electrons in its outer shell, and it would have to expend too much energy to either gain 4 electrons or lose 4 electrons. So what does it do? It shares them. And it does that through covalent bonding. It doesn't form an ionic compound, an ionic molecule. It actually forms, an ionic compound, it actually forms a molecule by sharing a covalent bond. Okay. And when it shares a covalent bond, we symbolize that there's something called the Lewis dot structure, or a line bond structure. This symbolizes that these are sharing electrons. This is showing the hydrogen sharing 1 electron, carbon sharing 1 electron. And this is showing nitrogen sharing 1, hydrogen sharing 1, and then these 2 electrons up top are known as nitrogen's lone pair of electrons. Those are his lone pair of electrons. He's not sharing those with anybody. So, for instance, if you look down here, he's not going to share those with anybody. He has those pretty stable. He has 3 bonds available, and then those are his lone pair of electrons. So that's how we do that. Non-bonding lone pair of electrons. That's just some basic chemistry that I don't want to get too much into, because as long as you know what that means, we'll move along then. Okay, so let's look at the valence bond theory really quickly. That just means that a covalent bond forms when 2 atoms approach each other closely and a singly occupied orbital on one atom overlaps a singly occupied orbital on the other atom. They are now paired in overlapping orbitals and are attracted to the nuclei of both atoms. They don't want to be too close because, let's see. So here's hydrogen. Okay, those are actually each just sharing an electron, but if they're too close, they would repel each other, and if they're too far away, there would be no attraction. So the bond length is the distance that leads to maximum stability. So, does it tell you what hydrogen H2's bond length is? And when they overlap like that, that's a sigma bond, which carbon and hydrogen also form a sigma bond. And then the bond strength is 436 kilojoules per mole. And do you guys remember your molar mass? Or do I need to do a video on molar mass? Because that was one of the most difficult concepts my when I was a chemistry tutor, people really struggled with that. Let's see. I don't know what the bond length is. I'm sorry. But the bond strength is how much energy you'd have to put in to break that bond, basically. I don't see what the bond. Oh, right here. Okay. 74 picometers C. So I think they've changed that now to angstograms. Okay. Alright, so we're gonna, I'm actually now to sp3 hybridization. And I'm gonna skip ahead to drawing chemistry structures, and then I'm gonna close out the book and I'm going to explain the hybridization to you in my own words, okay? I'm gonna draw it out for you. Is that okay? Okay, great. Alright, so this is showing you that when you draw carbon structures, carbon atoms aren't usually shown. It's assumed that a carbon is at the end of each line. At each intersection of two lines and at the end of each line. Occasionally, they'll put a carbon there for emphasis. Hydrogen atoms bonded to carbons aren't shown. Since carbon always has a valence of 4, we mentally supply the correct number of hydrogen atoms for each carbon. Atoms other than carbon and hydrogen are shown. For example, this hydroxide, RH, or whatever. Okay, so let's look at this. We know that they're not going to show a C at the end of every line or double line. We're just assuming that it's there. And that at the end of every C, there's also an H. So we can count how many C's are there. 1, 2, 3, 4, 5. And then we look over here. Yep, there's 5 C's. And every C, okay, this C already has 2 bonds to this C. And how many bonds can carbon have? 4. So that means it's bonded to 2 other H's. Okay, that's 2 H's there. Right, this C is 4 bonds already. This one is 4 bonds. This one is 2 H's, and this one is 3 H's. Oh wait, I'm sorry, this one only has 3 bonds. Well, you get the gist of it. You would have to go through and like calculate how many bonds each carbon has already to figure out how many hydrogens is connected to each, because carbon always has 4 bonds. So that's how the skeletal structure is drawn out to save time. And I wish we had time to practice some, but we don't. We're gonna move on. And next week, or next video, next chemistry video that I do, is going to be on polar covalent bonds, acids, and bases. So we're really going to be getting into organic chemistry. This was really just an introductory video. I really want you guys to let me know what you liked and what you didn't like, so that when I move on to the next one, you know. I'm going to first look at sp3. Hybridization. Okay. And this is CH4, or methane, that we're going to look at. Okay. structure. Lewis dot structure. It's something like this. And these are all equivalent. How is this possible? Let's look at the energy of carbon's shells. Right? We know that 1s has, okay, and let's look at 2p. Remember how we fill them in like this. This is what carbon 1, 2, 3, 4, 5, 6. So we know that these two orbitals, 2s and 2p orbitals, are not equal in energy. All right. But we know that all 4 of these bonds are identical. How is that possible when these are not equal in energy? Well, carbon does something. We're going to leave 1s out of it, okay? It's 1s is stable, but it goes into an excited state, okay? In which one of its s electrons is promoted up to the p orbital, and then its entire s orbital is promoted, and its entire p orbital is demoted to where they are actually. This is the excited state here, in which this electron moves up. Okay. And then now we have the orbitals become on the same plane, on the same, plane, and S is promoted, D is demoted. And S takes some of the P character, and P takes some of the S character. And that is called hybridization. They meld together, and they are no longer S and P. They are now sp3, 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 and they are all each seeking an electron. Okay. And this 3 means the number of p orbitals, not the number of electrons. And let's look at the shape. We know that S is shaped, S orbital, as I showed you, is shaped like this, and the P is shaped like this. So when you put them together, they're gonna look like this. Okay. And if there's 3 P's and 1 S, they're gonna be 75% P character, 25% S character. Okay? Alright. Now, think about it. Let's talk about drawing it out now. Okay, let's think about this. Here's carbon. We're actually going to ignore this little smaller piece here, and we're going to tuck it behind the C. Here are its 4 even orbitals, and they all have an electron at the end. They all have an electron at the end. Okay, we know that. Where is H's orbital? H's orbital is in, where's H's electron? It's in the S orbital. So the H has its electron like that. So here come all the H's. Oops, I did that wrong. I should be like this. Okay. Like that. There's methane. Now this right here is a sigma bond. Okay. And this is 436 kilojoules per mole in strength, this bond. Alright. And the bond angle in methane, this angle is 109.5 degrees. And so it's that diagram I showed you where it had like age, and then there's like one going into the back and one coming out the front of the page, and that would be the shape of it. Alright. Now we're going to look at another sp3 example. We're going to look at C2H6 ethane, sp3. Alright. A line structure for this is going to be, so carbon can have 4 bonds, right? Bonding to each other, bonding to another carbon, and then to 4 hydrogens. Okay. So each carbon is going to have its sp3, and it's going to have its sp3. Like that. So it can still each carbon in ethane has 4 single sigma bonds that is sp3 hybridized. So the sp3 bonds, they overlap with each other head on, just like in methane. Oh, sorry, that was... And they form, this is a sigma bond, okay? So they will form sigma bonds with hydrogen's s orbitals, and they will also form sigma bonds with the other carbon's sp3 orbital. So there's ethane. And it's important to note that sigma bond equals free rotation, because we're going to get to a different type of bond in just a moment. The bond length here is 1.5 176 kilojoules per mole between the carbons. Between the hydrogens, it's 423 kilojoules per mole. Okay. Now we're going to get on to sp2 hybridization. So if sp3 hybridization was between 2s orbital in carbon and all three of the p in the 2p orbital of carbon, what do you think that sp2 hybridization is going to be? You are correct. It will only be 2 of the p's and the 2p orbital. What's going to happen to that other p? We'll find out. Something really cool, actually. So, we're going to look at sp2 hybridization, and we're going to use ethylene. All right. The chemical structure is S2H4. Well, how is that possible to only have 4 H's when there's 2 carbons? Because there's a double bond. Now, this is shaped a little differently. It has a planar shape, and its bond angles are 120 degrees instead of 109.5. Okay. The carbons are sp2 hybridized. The strength of this bond is actually 728 kilojoules per mole. That's a pretty strong bond there. Let's look at what's going on in the energy levels. We're actually going to skip ahead to the excited state. So we're not going to show how the 2s electron goes up into the third, the 2p y or whatever. It's already there in our mind, okay? We're actually just gonna know that it's there. We already assume that it's been shared. Okay. See, we're gonna show that it's already shared. We're already gonna start in the excited state. This is gonna be promoted. Only 2 of these are gonna be demoted. This one isn't. This one's gonna stay. Okay? He's gonna stay. And then we're gonna have the S, and this S was promoted, this 2S, this 2P, and this 2P was demoted. And they hybridize and become 2S. I'm sorry. I'm sorry, that 2 does not need to be there. That's an S. Wow, I just totally butchered that. That's a sp2, sp2, sp2. Okay. This is the number of P's. We have 2 P's and 1 S. Okay. This P, he stays. He does not get hybridized. Alright, this P orbital is untouched. So we have 1 S and 2 P's, and they turn into this. We're still going to ignore the smaller back lobe. We have 3 of these. 1, 2, 3. They're shaped like this. They hybridize into a shape like this. In methane, we had 4 of these. I did not say that. They have 33% S character, 67% P character. since they have a little bit more S character than methane, they actually have less P character than methane because they have one less P. They're a little bit denser because this is a little bit more dense than this, which means that the bond length will be a little bit shorter. Okay, so as the hybridization includes less and less P character, the bond lengths get shorter and shorter. Something to think about. Okay, so now let's see what this fellow looks like. We have C, and I need a different color actually to draw. I'm going to use this to draw my non-hybridized P. See if that works. So here's a hybridized. Here's C, and here's hybridized, and hybridized. H is going to come along here. Yes. Now, here is a P. Oops. Here's P that is not hybridized. So remember how the P is shaped like this? And when it doesn't mix with an S, it doesn't turn into this where you ignore the back lobe. It simply just stays like this. When these two melt together mathematically, this all combines with this, and it all comes to the front, and you ignore this little back lobe. But when P is by itself, you have this lobe down here too. And so this and this form together, and this is actually called a pi bond. And there is no free rotation. This is not overhead lapping. This is side by side. This is a sigma bond, which is overhead bonding, in which there is, and this is 1.34 picometers or angstograms. Double bonds is shorter, electron density causes this. And so that is ethylene. Let's look at acetylene. It's an sp hybridization. What do you think that means? Do you think that means that we've got a 2s and only one 2p electron? You would be correct. So what do you think happens to the two non-hybridized electrons in the 2p orbital? Do you think they form a triple bond? You are correct. You guys are so smart. Alright, let's look at ESP hybrid. I didn't like how the book explained this, to be honest. The pictures in the book were all bubbly, and so I figured figured drawing them was a better way. Here is acetylene. Oh, sorry. You know, I thought I would be better at drawing them if I could actually get my atoms correct. I'm sorry. So oh wait, that is correct. I'm sorry. You guys, I'm really sorry. I haven't actually done organic chemistry in a long time, so thank you for being patient with me. Okay. Alright. Now, this is sp hybridized. This is not sp2 hybridized or sp3 hybridized, and this is not planar or 109 degrees. This is linear, 180 degrees. I feel like restarting this. Okay, so sp hybridization of acetylene. Okay, S2H2 HC123 CH, and this is not planar or 109.5 degrees. This is linear and 180 degrees. Okay, we're going to start in the excited state again. This arrow indicates the energy level, by the way. I don't know if I indicated that on the first page. But we're going to start with 2s. Like I said, we're ignoring 1s. We're just looking at the shell number 2. We're looking at the orbitals in shell number 2. And we're looking at okay, and we're looking at S, and we're going to just move these, and so we're going to have S and P, and then we're going to have 2 P's that we leave alone, and so we have SP and SP. Okay. One p orbital because we only need 2 hybrid orbitals because carbon bonded to 2 atoms. We're promoting 1 s orbital and demoting 1 p orbital. 2 p orbitals are left behind. Okay, so we then have 1 s, 1 p, and we're still ignoring that smaller lobe. We have 50% S, 50% P. This means that this electron density is even greater because we have the most S character here. Shorter bonds, shorter hybrid orbitals here. Okay, now let's draw this out. C, and we're gonna do, here's the, we have 2 sp orbitals, here's C, sp orbital, sp orbital. Here's our sigma bond, okay, and another sigma bond. We have 3 sigma bonds. Okay, 3 sigma. Okay, and we're gonna have 2 pi bonds because we have 2. Oh, I'm gonna do the these are the p orbitals that are not hybridized. Okay. So here's a pi bond here. And here's a pi bond here. And so, in case you're wondering, acetyl has no free rotation because of the pi bonds. Okay. A triple bond always has 2 pi, 1 sigma bond, and no free rotation. Bond length is 120 picometers or angstrograms. And I don't know if I mentioned this. A double bond will always have a double bond. Always have 1 pi and 1 sigma. Anytime you see a double carbon bond, there is a sigma and a pi bond and no free rotation. Anytime you see a triple bond, there's 2 pi and 1 sigma. Okay guys, so like I said, this was, other than the general chemistry tutoring video I made like 2 years ago, this was my first stab at organic chemistry. So tell me what you like, what you didn't like. Did you like the note section? Okay. Did you like the example homework problem that I did? Did you like the book? Do you want to see more of this? Because I will do chapters, 2 through 5. And so let me know. And when I do chapters 2 through 5, I'd like some feedback for you guys. Yeah, let me know what you think. And so I know this was a very basic video, and if there are some concepts you didn't understand, if you need me to explain them before I move on to chapter 2, or if you just want me to move on to chapter 2, let me know. And thank you.